Okay, so hi everyone, and welcome to this week's talk as part of the IISc MSR seminar series. We are glad to have with us Dr. Aravindan Vijayaraghavan, who's going to speak on finding adversarially robust representations. Dr. Aravindan is currently an associate professor in the CS department at Northwestern University. His research interests are in designing efficient algorithms for problems in machine learning, high-dimensional data analysis, and combinatorial optimization. In particular, he's interested in using paradigms that go beyond worst-case analysis to obtain good guarantees on algorithms. Prior to joining Northwestern, he was a postdoctoral researcher at NYU and Carnegie Mellon, and he obtained his PhD from Princeton University. So, yeah, with that bio, I guess you can begin.
Yeah, thank you very much. Yeah, thanks a lot for having me in your seminar series, and it's really nice to see a lot of familiar names and faces. And I also wanted to say that, so I'm very happy to kind of take questions in the middle of the talk. I haven't used Teams before, so I might not be paying as much attention to the chat, but please feel free to just unmute yourself and ask questions at any point in time. Yeah, so can you see my screen?
So I guess you'll have to minimize the Teams window because yeah.
Okay, good.
So
you can see the screen
there
now.
are a couple of black rectangles which are blocking because of the window, I suppose.
I see. Is it a little better now? Or
so there's still one more rectangle which is blocking some part of your slide.
Okay, in the bottom left corner?
Bottom left and in the middle sort of right. Middle bottom right.
Oh, really? Okay. Okay. So well, let me see if okay, does it remain the same in the next slide as well, or?
Yes.
Ah, okay. Okay, I don't know what this is then. Sorry, I should have checked. Should I? Does it help at all now?
So this removes one of the rectangles, but there's another one.
Okay, can you tell me where it, yeah, but can you tell me where it's blocking? Like there are three names and photos and things, so.
Yeah, so it's just below the middle photo. To the right of it slightly, yeah. It's actually blocking the name of the person in the middle.
Oh, Shwechen, okay. Interesting. So should I just try sharing again? Stop sharing and sharing again to see if that works?
Yeah.
Okay. Yeah, sorry, I didn't realize that. Is it any better now, or is it the same?
Yeah, it's still this. There are two rectangles which are blocking the view.
It's very strange. I don't see that rectangle. I mean, I can account for one rectangle because it's the view that I see of the small box that I see of you all. But then I don't see the other rectangle at all. So is it any better now by any chance?
Yeah, so one rectangle has gone away now.
Okay. So maybe if it's blocking out any text, you can let me know and I can try to explain. I mean, yeah. Unfortunately, I don't know what is missing, but hopefully if you can let me know if there is something critical that is missing, then I can read it out. Okay. So, yeah.
Do you want to go out of full screen and come back on full screen? Maybe that'll help.
Okay, I can try that. Yeah. 1 second. So first I should stop sharing, right?
Yeah.
Okay.
And are you sharing via this PowerPoint live option? When you go for sharing, does it show a submenu with PowerPoint live?
Oh, I see. So so first what I did was I put PowerPoint in full screen mode. That's fine, right? Or
yeah, that should be fine.
Okay, so let me do that first. And now
it might better to do it in the other way. So you put this sharing screen, this up arrow in the box,
Okay.
select PowerPoint, and then go to full screen.
I see. Okay, I'll do that.
Yeah, let's see how many PhDs does it take to.
Yeah, that's yeah, that should be. Is it any better now?
Yeah, so just the one rectangle now, which is probably the Teams window, I suppose.
Oh, okay, that's awesome. Okay, then I at least know what is blocking. Okay, great. Okay, thank you so much, everyone. Yeah. Okay. So yeah, so I thought I'll give you more of an overview of some research problems that I've been thinking about related to adversarial robustness and robustness in machine learning. This is based on joint works with mainly with Pranjal Avasti, who's at Google, Shui Chen, who used to be a postdoc at Northwestern and is now faculty at USTC, and Vagos, who is currently a postdoc. He split his time between Northwestern and MIT, and he's going to start a faculty position at UC Santa Cruz, and a few others who I'll mention along the way. Okay, so yeah, and as I said, please do feel free to interrupt me at any point in time. I don't intend to go through all my slides, so yeah. I primarily want to convey a flavor of the kind of nice questions that come up in this space and the rich connections it has to things that you may have already encountered and seen before. So the primary motivation of the talk comes from this notion of adversarial robustness, which you may have already seen or heard about, or really the lack of it that is there for modern machine learning systems. And this was something that was first pointed out in this really famous work by Christian Szegedy and others, where they showed that even if you take these really sophisticated image recognition systems, so these deep neural networks that achieve extremely high accuracy, you can make really, really tiny perturbations to these images, and these perturbations are adversarially chosen; they are not randomly chosen. And these ML systems start performing really badly. So for most images, you can come up with a very, very tiny perturbation of it, for which the classifier just classifies it completely incorrectly. Okay, and it seems like many machine learning systems, including very sophisticated classifiers, are not robust to these kind of really tiny perturbations. Whereas it's somewhat unsatisfactory because human vision seems much more robust to these kind of imperceptible changes. Okay, and this is not just true in vision. It has been by now demonstrated in many different domains, including audio, and there's like this famous example which is used to demonstrate why this is a security issue as well, about how with a self-driving car, it may not necessarily recognize a stop sign if you just slightly perturb the image, and that would be really bad for a self-driving car, of course. And yeah, it's been demonstrated in many different domains, and often the small perturbation to your image, it corresponds to really like a small change to your input vector, and this change is usually measured in some L infinity norm. For example, for images, you can think of changing each pixel by a small amount. Or sometimes people measure this in L2 norm or norms that go between L2 and L infinity. So in general, an LQ norm. Okay, so that is what we would normally think of as being a small perturbation. Okay, there's been a lot of work in this topic, starting with this work by Christian Szegedy, and I think there's been a lot less theoretical work to understand how and when you can train good robust classifiers or robust representations, and this talk is going to be about some of the theoretical considerations involved here. Okay, and this is in contrast to so these kind of things are talking about robustness at test time. You want to see how well a classifier does when you're making a small change to your test input. Okay, which is what you're doing at deployment. Okay. On the other hand, a topic that's received a lot of attention, particularly in the TCS community in the last 10 years, is robustness at training time. I mean, the fact that it's training time versus test time is not super crucial. I mean, here you typically think of either a learning algorithm or you're either training a classifier or you're trying to find some structure in data, and you perhaps have very good algorithms if your data comes from a really nice distribution. And then you also want your guarantees to be robust to noise and corruptions. Okay, and usually the way people study corruptions and this notion of robustness is to require that your algorithm continues to work well even if a small fraction of your data is corrupted arbitrarily. So maybe 99% of your data comes from this nice model, but 1% of your data is just outliers, corrupted data, and you want your algorithms to still work well. And even for basic tasks like mean estimation or clustering and things like this, I mean, these questions become very, very interesting, and there's been a lot of beautiful work in this topic. But the kind of questions that I'm trying to explore today are a little different because it's perturbations of a different flavor. So typically in this whole body of work in robust statistics, you care about what happens when a small fraction of the data is corrupted arbitrarily. Here, on the other hand, with adversarial perturbations, the way you should really think about it is that potentially, I mean, even if you're thinking about perturbations at training time, you should really think about every point as being potentially corrupted, but by a small amount. Okay, so these are, in some sense, very, very different in flavor because the robust statistics literature talks about what happens when a small fraction of the data is corrupted, but arbitrarily. So there's no bound on the amount of corruption, sorry, the magnitude of the corruption. Whereas with perturbations, every point could be corrupted, but you bound the magnitude of the corruption. Okay, so this actually leads to problems of a very different flavor, and that is what we will see in the context of a few different problems. Okay, and this is motivated by adversarial robustness, but in fact it also has motivations from other new emerging paradigms in machine learning. One such paradigm is this notion of low precision machine learning, where people have observed that when you're doing training with huge volumes of data, you actually get a lot of you can get a lot of memory and time savings by using low precision arithmetic only, so just 8-bit arithmetic to represent every number. And you of course gain a lot in terms of how much you need to store and running time savings as well. And this actually allows you to train much bigger models, which end up achieving much better accuracy. Okay, so there's a trade-off, of course, in terms of what is the precision that you use for your arithmetic versus the size of the model, right? And it turns out that even with low precision arithmetic, you can train much bigger models and achieve much better accuracies. And it's very natural for, yeah, sorry, go ahead, yeah.
So I had a question on the previous slide. Were we talking about, let's say, a supervised training data where epsilon fraction is incorrectly labeled kind of thing, or even in unsupervised setting where there's a perturbation to the
great question. In fact, in both these settings, you can ask this question, and it's really a big body of work. You can talk about this question both in the context of supervised learning and unsupervised learning. With supervised learning, it's a little more standard because it would correspond to what is known as agnostic learning, or a non-realizable setting where there's a classifier that doesn't fit all of your data well, but fits 90% of your data, in which case that would correspond to the error of the classifier. 10% would be the error of the classifier. In unsupervised learning, it's a little less standard, but now there are lots of works that do this. But you can think about, for example, if your data just comes purely from a Gaussian, you just want to estimate the mean, you would just take the empirical mean. But even if it's a one-dimensional distribution, let's say 10% of your data is corrupted, then that 10% of the data could be really, really far away, and it could skew the empirical mean. So in that case, you would want to use something like a median. Okay, and in high dimensions, this becomes much more interesting. So, so yeah, you could ask about these questions both in the context of supervised learning and unsupervised learning, and there are lots of different techniques and tools that people have come up with to deal with these scenarios. Yeah, so that's a great question. Thanks. Yeah. Yeah, so with low precision arithmetic, again, you can actually capture this precision error by some bounded L infinity perturbation to the points, because every value is corrupted by some value delta, which corresponds to the the least significant, which corresponds to this precision or error. Okay, so so broadly, the goal is to design various kinds of algorithms for basic primitives in machine learning and data analysis that are robust to these kind of adversarial perturbations. And we will be thinking about dealing with getting robustness to adversarial perturbations at both test time and training time. And I'll instantiate these things specifically in the context of learning representations, and maybe we'll think about the most simplest problem in this framework, which is just finding low dimensional projections, or PCA. Okay, so we are going to look at how to get robustness to adversarial perturbations, and we will focus on these perturbations measured in L infinity norm. You can explore the same question. Many of the results that I'll describe will also work for any LQ norm going from 2 to infinity. But I think it's most interesting when you explore this in the context of the L infinity norm. Okay, so you can ask many of these questions for your favorite machine learning problem, but we'll focus on what you do when you're trying to learn representations from data. So this is an unsupervised learning problem. Okay, and maybe the main takeaway from this talk is perhaps that I'll give you, I hope that you'll get a sense of how there are very interesting learning problems that arise even for extremely standard and simple settings, which are completely well understood when there are no robustness considerations. But when you do have these considerations of robustness to adversarial perturbations, you get extremely interesting algorithmic and statistical problems that have rich connections to things that have already been explored as well. Okay, so hopefully this gives you a flavor of that. Okay, so we'll be talking about finding representations of data, and in particular adversarially robust representations. So what do I mean by that at a high level? Okay, so you have some space of points, and you want to get an embedding of these points in some representation space. Okay, and you think of G as being this embedding. Okay, so this is what you usually want to do, but here you also want your representation to be robust. So what do I mean by robust? So what I mean is that when I look at 2 points, x and x prime, and suppose they are close, x and x prime are close, let's say an L infinity norm, then I want the representations of x and x prime to also be close. Okay, so in 2 norms here, because that's the norm that we are most comfortable working with, and that's the norm in which most objectives are formulated as well. Okay, so if you think of x prime as a small perturbation of x, then you really want the representation of x prime and the representation of x to be very close to each other. So as a illustrative image, so you want this representation of this image of this duck image with some small perturbation to be very close to the representation of the duck image itself. Okay, and this is something that you could think about in the context of any representation. But then these kind of representation learning problems become very challenging when they are nonlinear, even without robustness considerations. So let's actually focus on perhaps the simplest problem of this flavor, which is just learning a low-dimensional linear projection. Okay, and that's the famous problem of PCA, which we know and understand really well in the absence of robustness. So let's just ensure that we're all on the same page with this problem. So you're given a bunch of points, A1, A2, A3 up to AM. So M points in n dimensions. And your goal is to find a projection of your data, which is of dimension at most R, that captures most of your data. So this is a bunch of points in n dimensions. You want to find a subspace of dimension at most R that captures most of the mass of your points. Okay, so the way you want to think of this as a projection is that you can just think of projecting all the points onto that subspace, and now you can just represent points using a basis for that subspace. So that would be the representation of that point. Okay, so in the absence of any robustness, you're given a bunch of points. You want to find a R-dimensional subspace. R, think of it as being small, and that's why it's low dimensional, such that you capture most of the mass of the data. Okay, and the way you measure the error is in terms of the projection error, which is the sum of the square distances between the points to their corresponding projections. Okay, and so this is the usual formulation for PCA. This is actually minimizing what is known as the Frobenius norm error. And we know that this is a polynomial time solvable problem. You can just use the singular value decomposition, truncate to the first R terms, and you will find the best rank R projection. Okay, and in fact, you could have formulated the problem slightly differently, where instead of minimizing the Frobenius norm error, you could also have minimized the spectral norm error, and PCA minimizes this as well. Okay, so it simultaneously minimizes both objectives. Okay, good. So there seems to be a question, or maybe I think Nabanita, you have a question. So it seemed to say that someone was asking for control. Maybe that was, I don't know if it was a question or if it was just by accident.
But I have a question.
Sure.
A here is the matrix with the AIs as columns, is it?
Oh yes. Thank you, Neeraj. Yeah, A is just a matrix where, yes, exactly. So yeah, A is just a matrix where, yeah, this capital AJ should have just been small AJ. Actually, I'm sorry about that, but A is just a matrix where the columns are the points. Okay, so oh, I see. So yeah, I guess I didn't really specify which way it goes, but yeah, let's for now think of it as the columns being the points. So it's n cross m matrix. Okay, so these are specifically these are small ages. Yeah, thanks. Okay, yeah, thanks, Neeraj. Any other questions?
Yeah, like the problem that you posed in the previous slide, would it not be just the continuity of G that assures us that? In the previous slide,
of G. Well, yeah. I guess you mean like some kind of a Lipschitz constant for the mapping, right? Perhaps.
That would do, yeah.
Yeah. Yes. In some sense, you are interested in how Lipschitz the mapping is, and you want a mapping that is very Lipschitz. And often these mappings don't necessarily need to be. I mean, if it is very non. I mean, if you think about things that come from neural networks and things, they don't even need to be differentiable and things. So you have to be a little careful. But yes, typically you are interested in things that look like the Lipschitz constant of the mapping. Yeah. But the problem is that, you know, these values, these exact values matter. And typically you want to think of Lipschitz constant as you're moving X in some norm. And I mean, you typically move X in a 2 norm, and you also want to measure the output in the same norm. Here, these norms could be different. And that's actually part of the challenge in this problem, because you want to think of the points as moving in L infinity norm, and you're measuring the output in, you know, how much the output varies with respect to if it's a function which has output dimension 1, then you're measuring Lipschitzness with respect to the L infinity norm. But in fact, the function could also be vector valued, in which case you have to measure that in some other norm as well. Okay, so but you're absolutely right. It is related to Lipschitzness of the maps, but it is a notion of Lipschitzness which depends on the specification of the problem. And you want your maps to be Lipschitz in some sense. Yeah. We'll precisely see what it actually corresponds to in just a bit. Okay, but currently the PCA problem has stated that there's no robustness as specified currently. Okay, but now we can add robustness. Okay, and let's see what robustness imposes as a constraint. Okay, so let's think of what does robustness correspond to for a low dimensional projection. So the representation of a point X just corresponds to that's given by this low dimensional projection is just the projector applied to x, so pi times x. That's the representation of the point x. Okay, that will give you the point on the subspace. Now, what does adversarial robustness here correspond to? Well, it says that if x minus x prime's infinity norm is at most delta, I want the corresponding projections to be close in 2 now. Okay, to be at most some kappa times delta, where kappa is some robustness parameter. Okay, it turns out that this robustness parameter kappa, which captures how robust this projection is exactly captured by, it's not very hard to see that this is exactly captured by what is known as the infinity to 2 norm of the projector. Okay, and it is a precise characterization. What is the infinity to 2 norm of any matrix M? It just corresponds to the it's infinity to 2 norm. So you look among all vectors y whose infinity norm is at most 1, and you look to maximize the 2 norm of the action of that matrix on y. Okay, so that is the infinity to 2 norm. Okay, and so here we are measuring this infinity to 2 norm for the projector pi, and it's not hard to see that this actually precisely captures robustness as measured in this way, in the sense that if you have a bound on the infinity to 2 norm, then you get an upper bound on this robustness parameter. But in fact, around every point, you can actually come up with a perturbation that exactly realizes this distortion in the in how much the projections move. Okay, so the amount of robustness of the adversarial robustness of this projector pi is exactly characterized by the infinity to 2 norm. Okay, so are there any questions about what the infinity to 2 norm is? Those who haven't seen this before. Okay, so if not, so this exactly captures the adversarial robustness, and what we really, and in general, if you want to look at robustness measured in LQ norm, you'll just be looking at the Q to 2 norm of the projector. Okay, and so now we can revisit the PCA problem. What do we want to do? We want to find a good low dimensional representation for your data. That's just finding a low dimensional projector. But additionally, I also want it to be robust. Okay, so for that, I just have the usual Pca formulation. I want to find a projector whose rank is at most R, that minimizes the projection error, that is the Frobenius norm of A minus pi times A. But in addition, I impose a constraint that pi's infinity to 2 norm is at most kappa, where kappa is just some robustness parameter that, yeah, I mean, is the amount of robustness for the projector. Okay, it's just a constraint that is additionally added. So this is the, I mean, you can think of this as the adversarially robust PCA problem. Okay.
Are there always solutions to this?
Pardon? Sorry.
Are there always solutions to this problem?
Well, as stated, you can always just pick, I mean, it's an optimization problem, and there are certainly feasible solutions. You can always pick pi to be 0 as well, right? So it's yeah, I mean, or pi to be any rank R subspace that'll give you some value. Among all such subspaces, you want to find the minimum error one. Does that make sense? I mean, does it answer your question? Or
yeah, yes, it does. Yes.
Yeah.
And are there values of kappa for which this is trivial, like maybe root R or something?
Yeah, exactly. That's a great question, Neeraj. So in general, you should think of kappa, and I'm going to come to that in just a bit. But kappa takes values between 1 to root n for infinity to 2 norm. Okay, for any projection matrix, kappa is going to take values from 1 to square root n. And if it is more robust, then it is closer to 1. Okay, so this is the range of parameters that you should think about, 1 to square root n. And if it is square root n, then it is really not any constraint. So it's essentially, you can look for any, I mean, any projector will have infinity to norm at most square root n. So kappa being square root n is essentially unconstrained. Okay. Yeah, we'll come to that in just a bit. Okay, so this is the question, and so without the robustness, so again here you can switch it with the spectral norm objective instead of the Frobenius norm objective, and here I kind of formulated this robustness thing as a constraint, but you could also, and the objective as being the projection error, but you could also switch the role of the constraint versus the objective, and that's something you could do too. And eventually we'll be looking for approximations, and we'll get approximation factors for both. So it doesn't matter which way you frame the objective or the constraint. Okay. Okay, so this is the adversarially robust PCA question. You want to find the minimum projection error among all projection matrices of rank at most R with a specified infinity to 2 norm upper bound. Okay. Now, it turns out that we will design up some approximate algorithms for this, and then it turns out that I mean, just like PCA is an extremely useful subroutine for many tasks, this adversarially robust PCA will also end up being an extremely useful subroutine for many downstream tasks, including actually making some deep neural networks more adversarially robust. Okay, and we'll see that in a bit. Okay, so just to go back to this question, so this is a standard PCA question, and this is polynomial time solvable, and now we have an additional constraint, and it turns out that this becomes hard, and we'll see how hard it is. Okay, but just to go back to Neeraj's question, let's see what these kind of robust subspaces look like, and to get more of an intuition of this infinity to 2 norm. Okay, so let's just focus on the setting when R is equal to 1. So you're looking at a subspace of dimension 1. Okay, so what does the infinity to 2 norm capture? So you can just do some simple algebra, which I'm not going to go into, but suppose you just think of your projection as just being given by V times V transpose, where V is a unit vector in L2 norm. Okay, then it turns out that the infinity to 2 norm is precisely the L1 norm of the vector V. Okay. So really, if you think about, and you know, for rank 1 subspaces or rank 1 projectors, pi is exactly of the form V times V transpose, where V is a unit vector. So the infinity to 2 norm for rank 1 projectors exactly captures the L1 norm of the unit vector. Okay, which is actually a notion of sparsity that's called, that is often called analytic sparsity. This is the ratio of the L1 norm by the L2 norm. Okay, so this is known as, this is some kind of a analog for sparsity of a vector. Okay, so this is just the L1 norm of V divided by the L2 norm of V. If the vector is actually sparse, then this value is sparse, is small. Whereas if it is very spread out, this value may be large. Okay, but it's a very nice way of capturing sparsity. Now this is for rank 1 subspaces. What about higher rank subspaces? It turns out that you can do a very similar calculation using duality of norms and so on. Let me just cut to the chase. It turns out that this infinity to 2 norm of a projector, this is, you can think about infinity to 2 norm for matrices, but specifically if you think about projection matrices, orthogonal projection matrices, then the infinity to 2 norm exactly captures the maximum L1 norm among all unit vectors inside the subspace. Okay, so if it was just one dimensional, then there's only one vector in that one unit vector in that subspace. So I mean up to sign. So that exactly captures the L1 norm of that unit vector. But if you have a whole subspace, you look among all possible unit vectors in L2 norm and try to find the one that has a maximum L1 norm. So it is also a notion of sparsity, but it is, it tries to find the least sparse vector inside that whole subspace as measured in the L1 versus L1 by L2 notion of sparsity. Okay, and and if you know that this subspace has if you can think of a basis for the subspace where all of the vectors in that basis are sparse, then it will give you a bound on the infinity to 2 norm with some loss in the dimension of the subspace. But I think the best way to think about it is the thing that I put into the box. Okay, so it's just a very nice way of capturing sparsity inside that subspace. Okay, and you know, this is something that people have done in statistics a lot. That is, people look at sparsity a lot, and there are questions like sparse Pca and things that people study a lot, and there are generalizations to of sparsity to higher dimensions, and often these different definitions of sparsity for higher dimensional subspaces, I mean, you know, not just vectors but subspaces, they often tend to be basis dependent, which is something that's a little annoying about these different notions. But this infinity to 2 norm notion is a very nice notion because it's basis independent and it's a very clean abstraction that's also motivated by robustness considerations. Okay, so yeah, so this tells you what the infinity to 2 norm is trying to capture, and in general, yeah, just from this characterization, you can actually see that the infinity to 2 norm can only be between 1 and root n, because the ratio of the L1 norm by L2 norm can be at most root n, and it's at least 1. Okay, so this is why the infinity to 2 norm is between 1 and root n. So if it is close to 1, then it is more constrained because all your vectors have to be very sparse, whereas a vector that's completely spread out will have this ratio being close to root n. Okay, and that will be fairly unconstrained. Okay, any questions?
Are there such nice characterizations for the Q to 2 norm? Or this
yes, good, great question. So yes, you can do the same thing for Q to 2 norm, where instead of you know, L1 norm, you would just measure it in terms of the Q star norm, the dual norm of V of Q. Okay, so this is the dual norm. So for L infinity, Q being infinity, Q star is 1. So you get the L1 sparsity. For LQ, general LQ, you get you know, LQ star. So yeah, I mean, you will be measuring sparsity in LQ star. So for example, for something like for Q being 2, you will get 2 itself. But you know, for things between 2 and infinity, you'll get some other norm that is between 1 and 2. So that is like a very, yeah, so all of these things just go through using duality and some norm duality, and so there are very natural analogs, okay, for any LQ norm. So that's a great question. Thank you. Yeah. So does it answer the question that you had?
Yeah, thank you.
Okay, cool. Okay, and yeah, so the bound on the Q to 2 norm will also be not necessarily 1 to root n, but you'll get some other thing that depends on Q. Okay, so maybe n to the half minus n raised to the power of half minus 1 over Q or something like this. Okay, okay, and now one natural question you may have is, well, is this even a natural constraint? That is, can you even hope for these subspaces to be robust in this infinity to 2 norm? It turns out that a lot of naturally occurring data are actually robust or sparse in the infinity to 2 norm, and if you just look at it in the right basis. Okay, so these kind of robust subspaces exist for real data. For example, if you look at images in the discrete cosine, I mean, in like the Fourier basis or things that look like the Fourier basis, then you will actually see that you will find a very low dimensional subspace that captures a lot of your data, and the subspace is actually very robust as measured in the infinity to 2 norm. So for example, if you take the Cypher 10 dataset, it has dimension which is around 1024. Okay, and if you try, you can actually project your data. It actually has a very good 2-dimensional subspace that represents it, and in fact, the subspace is robust as measured in the infinity to 2 norm as well. So typically, you should expect the infinity to 2 norm to be at most the square root n becomes 32 for 1024. But you see that the infinity to 2 norm is actually much smaller. It's close to 20. Okay, so that is substantially smaller than 32. These are all small numbers, so you don't see, I mean, if you're an approximation algorithms person, these are all within factor 2, so 1.5 of each other. But in practice, it's actually a significantly smaller number. Okay, so you do expect real data to have these robust low-dimensional projections. And so our goal is to find one such low-dimensional projection which is robust for your given data. Turns out that this problem is actually not very easy once you have this additional robustness constraint. And that's true even when the rank is 1. Okay, so let's even focus on the rank being 1 and Q being infinity. That's the infinity norm. Here you just want to find one direction which captures as much of the data as possible, and you want the direction to be sparse in the L1 sense. Okay. Now, so if you just write down the objective and you just do some algebra, you just see that the complementary problem is this problem, which tries to maximize this quadratic form. Okay, it's like an eigenvalue style problem where you just want the direction to also additionally be sparse. And this is a well-known problem that's been studied in statistics a lot. This is called the Sparse Pca problem. It's a maximization variant of it. And instead of just measuring the sparsity in the L0 norm, which is what people usually do, you're measuring the sparsity in the L1 by L2 norm. And this is the usual notion of sparsity. This is combinatorial sparsity. And you see that it's related to the combinatorial sparsity. Okay, that's a L1 by L2 sparsity. And this problem is actually very hard. It's notoriously hard. It seems to be, the best known approximation factor is like an n to the 1/3 approximation, but that's for the maximization version. And it turns out that you can use the hardness of this problem to also show that the problem that we care about is also hard. Okay, even though that's a minimization problem, it doesn't give you an approximation hardness, but it gives you some hardness. Okay, and going between this L1 by L2 sparsity and L0 sparsity doesn't actually lose too much of a, it doesn't change the problem substantially. Okay, so these are very related problems. Okay, so the upshot so far is that we have this adversarially robust Pca problem. It seems like a well-motivated problem, except however, the issue is that when you have this additional adversarial robustness consideration, it becomes hard. Okay, because it's related to problems like sparse Pca, which are quite hard. Okay, so what can we show for this? We can show a bicriteria approximation. So let's say that opt is the optimal rank R projection. It has robustness at most kappa, and it achieves a projection error of opt. Then what we can give is a polytime algorithm, which will return a rank R projection, which violates both, which kind of loses a constant factor in both the robustness parameter and in the projection error. Okay, and that's a bicriteria in the sense that if you can get your projection error to be as close to 2 times the optimal value as possible, but you will lose a corresponding constant factor in the robustness factor. Okay, so in general, if you just set this gamma factor to be a constant, you get a constant comma constant bicriteria approximation. So this problem is hard in the worst case, but you get a constant comma constant bicriteria approximation in polynomial time. Okay, and this is in the worst case. You can also get a similar statement for the spectral norm objective. It turns out that when you have robustness considerations, if you don't have robustness considerations, Pca simultaneously solves both problems. Okay, of finding the lowest projection error in Frobenius norm and the lowest projection error in spectral norm. But when you have robustness considerations, these two solutions may not be the same. And in fact, we designed different algorithms for these two different problems. And for the spectral norm objective, we get something like a 3-factor approximation instead of a 2-factor approximation. And just to contrast this with, we saw the maximization problem, and we saw that had an n to the 1/3 approximation. And in fact, there is no better algorithm known. It seems quite hard to get subpolynomial approximation factors. On the other hand, if you look at this minimization version, you can actually look at much higher ranks. You're not constrained to rank being 1. You can go to much higher ranks, and you can actually get a constant comma constant bicriteria approximation. Okay. Good. Any questions about the result?
Hi. Sorry if this is a sort of basic question, but is there any way to relate these the rank as well as the robustness factor? Like, can you say there is some gamma which is good? Because they seem quite interesting to have related approximation.
So, I see. So you're asking if sorry, if I understand your question correctly, are you asking if the rank is related? I mean, if the approximation factor depends on the rank? Is that what you're asking?
Yeah. So I think the rank is unrelated to the robustness factor,
Yes.
but the approximation factors are related. Therefore, like, is there some way of can you choose a certain approximation such that you kind of fit both?
Yeah, so actually maybe let me try to say the following. I don't know if it helps. So the approximation factor, there are two approximations involved here. Okay, so forget this result for now. Just focus on this result, okay, that I've labeled in the box. So this will always find a rank R projection. It doesn't actually does any approximation in terms of the rank. And this factor in the approximation does not depend on the rank either. So the two approximations that are involved are in the objective function, which is the projection error, and in the robustness factor. Okay, so this is the robustness factor. There is no relaxation in terms of the rank. Okay, the rank is still going to be rank R. The later statement that I said is just that if you want, you can also get arbitrarily close to 1. Here you get a 2 plus gamma factor, but you can get close to 1 plus gamma factor by also relaxing the rank a little bit. I don't know if this is necessary.
Yeah, that sort of answers the question.
Okay.
Yeah,
good.
that sort of answers the question because once you.
Yeah. Okay. Great. Okay. Yeah, and in general, actually, to be honest, I don't even think the problem, even when R is equal to N, is still an interesting question. So it's not like, just finding a robust projection, even if you don't limit the rank, is still interesting. I don't actually know how to get an algorithm for it without this result. So it's getting a robust projection that seems very challenging in general. Okay. Okay, so and this is when you're given a bunch of points and the projection is supposed to be robust. That's an external constraint that we are adding. But additionally, because the projection is itself robust, we can also tolerate some adversarial perturbations to the training data itself. That is what I mean by that is maybe the given points A1 to AN are not the right points. You're given some perturbations of these points. Okay, you're given A1 tilde, A2 tilde up to AM tilde, which are themselves off by some amount. And you can still run the same algorithm, and you can actually use this algorithm to get a good projection for the unknown uncorrupted matrix A itself. Okay, so even if your data itself was corrupted to begin with, you can actually you can use these ideas to get a good projection for the uncorrupted data, even though you have no access to it. Okay, so that's something that you get almost as a byproduct in some sense. Yeah, I mean, you need a little bit of work, but you get it as a byproduct. Okay, so the same ideas also help for training time robustness. And you can also ask, well, in some sense, you want, I mean, even if you did not care about eventually finding a robust projection, if you just cared about training time robustness, which is I have my data, it could have been, the given data could have been potentially corrupted. I want to find a good low dimensional projection for the uncorrupted data. Okay, you could ask, well, does it actually need to rely on these infinity to 2 norms that we have been looking at so far? And you can actually try to understand this for not the worst case version of the problem. That's a little hard to reason about, but you can think about a very natural average case version of the problem, which is something that people study a lot in statistics. It's called the spike covariance model. And that's the formulation in which even the Sparse Pca problem has been studied a lot. And it turns out that you can actually use the same algorithm to find good the principal component or the principal subspace for your data in the spike covariance model Okay, so here in this model, your data is looking like a Gaussian, except that there is a slightly higher covariance along this particular subspace, and that's the subspace that you want to find. Okay, that's the principal subspace. If you don't have any robustness considerations, you would just do PCA. But with if your data could be corrupted, it turns out that the right thing to do is to exactly place a constraint on this infinity to 2 norm or the Q to 2 norm and find principal component with this additional constraint. Okay, and it turns out that even if so this is what you should do algorithmically, and you can get a good guarantee for the recovery error of the subspace. Okay, that depends on the infinity to 2 norm or the Q to 2 norm in general. So it turns out that this is almost an instance-wise optimal guarantee. So for every projection pi for every subspace pi star that you care about, there is like a fundamental limit which exactly corresponds to something that involves this infinity to 2 norm. Okay, so what this is really saying is that even if you don't worry about even if you only worry about training time perturbations, if you look at this very classic average case model, it illustrates why this infinity to 2 norm is somehow fundamental to getting robustness to these kind of perturbations measured in infinity norm. Okay, because you can get an instance-wise optimal guarantee. Your algorithm gets a guarantee, and you can actually get a lower bound for every instance that essentially matches the guarantee up to some polylog factors. Okay, okay, so that's just something that I just wanted to kind of bring out this fact that this infinity to 2 norm comes out very naturally, and it's somehow important for this problem in terms of getting this robustness to adversarial perturbations. Okay, and maybe I'll skip this slide. It's just to give more intuition about this infinity to 2 norm. And maybe I already gave some intuition about this. It's just a very nice way of capturing sparsity of your subspace. Okay, so actually, I guess I don't have that much time left. So let me also just briefly run over this. I just wanted to say that you can actually use these ideas to get certified robustness even for neural networks. These are linear projections, right? So PCA is trying to get a linear projection, but you can use this as a subroutine, as really like a first level filter in some sense. The bottommost layer, you use this robust PCA subroutine that we have designed, and you can actually use it to train neural networks that give you much better robustness. You can actually give some provable notion of robustness for neural networks that is better than what you could do without these robust projections. And this is using, we use a known technique called randomized smoothing, which is a very nice idea to get some certified guarantee of robustness for neural networks. So what a certified guarantee means is that you will output a neural network, and it will be guaranteed to not change its output in any ball of radius up to some r of x, which is specified. Okay, there is an approach that tries to, you can kind of try to smoothen the classifier to bring down the Lipschitz constant, and that gives you some notion of robustness. And it turns out that that's the way by which people get robustness even to L infinity norm, which is what people care about a lot. And you usually lose a large dimension dependent term in translating guarantees from L2 to L infinity norm. But by using this robust primitive, you can actually replace the square root n loss by a loss that actually depends on this nice robust projection that you found. And the square root n just gets replaced by square root kappa. And this actually gives a much better guarantee. Okay, so for example, this is a follow-up empirical paper that we had in NeurIPS, where we were able to use these kind of robust projections for images to obtain, to train more robust neural networks. Okay, maybe just in the next 5 minutes or so, or even fewer, let me give a rough idea of the kind of ideas that are involved, techniques that are involved to get these constant factor approximations. The main idea is using a convex relaxation or a semi-definite program, really. And the way you do it is to relax this projection that you're trying to find, this rank R projection, you relax it to instead find a positive semi-definite matrix. So that will correspond to a semi-definite program that you're trying to solve. And there's a very natural way to do this. Okay, so if you just look at this version of the problem without any robustness, this is a semi-definite program that whose solution exactly turns out to be the top eigenspace. Okay, so exactly corresponds to SVD and truncation to the top R eigenvalues. Additionally, you want to place a constraint. So this is a STP relaxation that exactly captures the Pca problem without any robustness. Additionally, we want to place this robustness consideration. It turns out that this robustness constraint, just enforcing this constraint is itself hard, because this corresponds to what is, so it is a convex program, which is nice, but implementing or checking this constraint is actually hard, because this corresponds to what is known as a Grothendieck norm. Okay, so this is related to this famous problem called the Grothendieck problem, and it corresponds to the Grothendieck problem for PSD matrices, and this problem is hard. So computing the infinity to 2 norm for a matrix, in fact, even for projection matrices, is NP hard. Okay, but what you can do is you can get a good approximate. You can get approximation algorithms for these, and we will use these approximation algorithms as a black box to give an approximate separation oracle for this relaxation. Okay, so but there's another challenge, which is perhaps the more important challenge, or the more interesting challenge. And here the issue is, you find this PSD matrix, this matrix that is potentially a solution, and from this PSD matrix may not be of rank R, and from this you want to get a rank R projection. Okay, so your goal is this PSD matrix may be of rank which is much higher, potentially of rank N, and from this you want to get a projection matrix of rank R. Okay, but you want to do this in a way such that the amount of robustness, this Q to 2 norm or the infinity to 2 norm, doesn't blow up when you do this, when you bring down the rank to R. A very natural way to bring down the rank from N to R is just truncation to the top R eigenvalues or top R eigenvectors. Okay, but by doing this truncation, you may potentially blow up the infinity to 2 norm or the Q to 2 norm. Okay, and that actually becomes an issue. And that's actually the main challenge that one has to deal with. And the main way we deal with this is using a fairly simple trick. But what we do is we identify that the main insight is that you can actually do this kind of truncation, and you can get much better control in terms of how much this norm increases, this Q to 2 norm and stuff increases, if there is some basic monotonicity property that the norm satisfies. So what is this monotonicity property that we care about? Well, it's just a very simple property. You want that, if you want this norm to satisfy this property, that if M2 is larger than M1 in a natural sense for PSD matrices, then the norm of M2 should be larger than the norm of M1. Okay, so what is this natural ordering of PSD matrices? This is what is known as the Loevner ordering. Okay, so this is just saying that if M2 can be written as M1 plus another PSD matrix, M2 and M1 are both PSD matrices, okay, then you would like M2's norm to be larger than M1's norm. Okay, and it turns out that if your norm that you're interested in, here it was the infinity to 2 norm, but if the norm that we were interested in is actually monotone, then you can go from this STP to actual projection matrix fairly. It involves some work, but it is not too hard. Okay, so that's because you can get some really nice control on how much the infinity to 2 norm or the norm that you're interested in changes when you're doing things like truncation or scaling and so on. Okay, and this is a very natural property that is true for things like the spectral norm, Frobenius norm, and any unitarily invariant norm. But however, it is not true for the Q to 2 norm or the infinity to 2 norm in general. Okay, when Q is not equal to 2. So that's one of so this is a nice property to have, but it is not actually satisfied by the norm that we are dealing with. But a simple trick that a simple observation that you can see is that that one can actually check is that instead of looking at the infinity to 2 norm or the Q to 2 norm in general, you can actually go to a slightly different norm which is very related to it. Okay, so you are interested in the, unfortunately I'm not able to write for some reason. Okay, so you are interested in the Q to 2 norm in general, or when Q is infinity, the infinity to 2 norm. That is not monotone. However, you can actually go to the Q to Q star norm, which is a related norm. Okay, which is, so that would be the infinity to 1 norm for when Q is equal to infinity. Okay, instead of the infinity to 2 norm. And this norm is actually monotone. Okay, and you can actually control the infinity to 2 norm by controlling the infinity to 1 norm instead. Okay, so this is a proxy that you can use, which is also monotone. Hello, is my screen moving or is it stuck for you?
It's on the same slide.
Okay, so for me somehow this, sorry, my slide isn't moving. Okay. I guess this is a very natural way by which it's, it's maybe PowerPoint's way of saying that time's up. I was anyway planning to wrap up very soon, but okay. Maybe let me just try sharing and going to the conclusion slide, but if it doesn't work, it's, I guess, that's what it is, yeah. Sorry, 1 second, let me just try this again. Oh, I guess PowerPoint is misbehaving. Sorry, I don't actually know why my my PowerPoint is hanging. Let me just very quickly reopen it, but I'll also conclude very soon. Hi, can you still see my? So let me. Can you see my screen now?
Yeah.
Hello?
Yes.
Okay, good. Okay, so yeah, I was just gonna say, let me just so instead you can just do things using the Q to Q star norm, which turns out to be monotone, and that's actually how so that's the STP that we will solve, and we'll run a fairly simple algorithm which just solves the STP and then does some simple truncation. Okay, it's just some work involved in picking this nicely, but yeah, the rounding is actually fairly simple. Okay, so let me actually conclude here. So in general, we saw this question of robustness to adversarial perturbations, and we explored this in the context of a very simple problem, which is PCA. And even here, it became quite interesting. It was related to sparse PCA and other variants. And you can actually use this to get algorithms for tasks like clustering, for tasks, supervised learning tasks like binary classification and things which are all robust to adversarial perturbations. And I also described how you can get robustness even in practice with certified robustness for neural networks. I think in general, notions like there are different notions of robustness that arise, and adversarial perturbations is one. And I think it gives rise to very interesting questions even for basic primitives that we understand extremely well without robustness considerations. And I think there are lots of questions to explore here. Yeah, so yeah, so I hope maybe it excites some of you to think about some of these questions as well. Okay, let me stop here. And I'm very sorry for going late and for the technical issues. Yeah.
Okay, so any questions from the audience members?
So Aravindan, you had mentioned sometime in your talk that you take an image and represent it in the DCT basis.
Yeah.
That tends to be sparse, and I didn't know this. And I'm curious, is there any intuition why that is so? I mean,
Yeah. So in general, I guess. Okay. So let's not. Yeah. So let's just think about the Fourier basis in general, right? Like. I mean, I don't know specifically why DCT is used, but for some reason DCT is used a lot in images. But I guess in general, I mean, yeah. So I think if you look at the Fourier basis or this DCT basis, maybe the first level, the first vector in that basis probably corresponds to things that look like the all ones vector. So that would correspond to something like the average of all entries, and then you have these kind of okay. So I guess what I'm trying to say is that it is true that even for images, if you think about, I mean, for audio, it's perhaps a little more intuitive that somehow a lot of your signal is in low frequency, is in is perhaps in the is in certain frequencies alone, and so you can kind of restrict your attention to those frequencies, and you still retain a lot of your signal, right? Whereas I guess apparently it's also true for images. I didn't. Yeah, so I'm trying to see if there is a very natural intuition for it, but for example, the primary component would correspond to the biggest component would actually correspond to just the all ones vector. Okay, so and that's just because your pixels are between, let's say, you normalize them. So let's say it's between 0 and 1. So you just take the average value of all the pixels and you just multiply it by the all ones vector. So it will have a large component along the direction. And then maybe there is like some, just because there's a lot of locality in your images, right? So you can think of maybe a portion of your image as being some average value plus some small variations in that local region. So I think these somehow seem to be captured really well by, these more global average values seem to be captured very well by the zeroth. The complete average is captured by the zeroth order coefficient in some sense. But then these larger scale averages seem to be captured well by lower frequency components, and these components themselves are actually very good. Yeah, I think the small variations in the image may correspond to high frequency variations, but they correspond to very small variations in that whole image. I don't know if this was the question that you were asking in terms of providing intuition for why this is true, but if you kind of find it natural that these so Okay, so what do you want for? So you want a nice basis where, so okay, so it's very natural that if you look at a lot of data looks sparse when you look at it in the right places, right? So that alone is not enough here because you actually want, I guess for you to have a good yeah, so let me try to see if there is a nice way to explain this. Yeah, so I think it turns out that yeah, okay. I don't know if there is like much better intuition I can provide for why images look like that, but actually let me go back to this plot and maybe that would help a little bit. So if you actually look at these principal components of just your data, forget trying to find robust components, just find all the eigenvectors of your data. Find the top eigenvector, find your, take a bunch of images, find the top eigenvector of your set of images for that matrix that corresponds to rows being images, then the second top eigenvector, the third top eigenvector, and so on. And you can just measure the L1 sparsity of all of these, right? So it turns out that their L1 sparsity itself is going to be around 20. It is quite small. It's much smaller than square root n. So this really tells you that the eigenvectors, the top few eigenvectors themselves are sparse. Okay, so it's this doesn't tell you that there is a subspace. So if you just look at the top, let's say 10 eigenvectors, right? That is actually going to give you, so it gives you a basis. That's a subspace, and this is a basis, all of which is sparse. As such, if you use the bound, you lose an extra square root 10 factor. But it turns out that all of these eigenvectors are also sparse with respect to the same coordinates. And you lose this factor of this extra factor of square root of the dimension of the subspace when these coordinates are disjoint. But if they are actually in the same, if they are all sparse in the same set of coordinates, then you don't really lose this factor that corresponds to the number of the rank of the subspace. So yeah, I don't know if that explains, gives some intuition, but yeah, this is how
yeah, just to make sure, you probably meant the singular vectors rather than the
eigenvectors. Yes, not eigenvectors. I meant singular vectors. Yes. Yeah, exactly. So if you look at the singular vectors of this matrix itself, each of these singular vectors are sparse. And yeah, that somehow I don't have very strong intuition for it, but I somehow think that it is a lot like audio, where maybe it's just some frequencies are very important, and those are the ones that, yeah, a lot of your signal is just captured by some few frequencies in your data. It seems like it's true for images too.
Any other questions?
Yeah, so I thought, the problem that you are solving, you eventually get a robust representation. Do you also the adversarial perturbation that causes the most problem? When I say causes the most problem, I mean which maximizes the infinity to 2 norm.
Okay, good question. So I guess maybe what you're asking is, okay, good. So you can find a projection matrix pi, right, which is which has a small infinity to 2 norm, and then maybe gets a lot of your signal as possible. And then once you find this pi, you can just run this grothendieck problem. This Yeah, you can run. I mean, it's an NP-hard problem to find the worst direction for a given projection matrix pi, but you can get a good approximate solution. So that's something that you can do.
Yeah. So basically, what I'm asking is, if I was the adversary rather than the algorithm, like, can I come up with good adversarial example?
Good. That's a great question. Yeah, actually, that's a very good question. I don't know if people have tried this to get. I mean, so there is a huge body of work. There's a whole community of people who work on these things where people come up with various attacks, and then people come up with defenses against these attacks, and then it's like a, it's like security research, right? So, and I don't know if people have used these specific directions to come up with interesting attacks. That is a good question. I haven't explored this, and I don't know if people have, but it sounds like a natural thing to do. Yeah.
Okay, if there are no other questions, maybe we can thank the speaker and yeah, conclude for the day.
Yeah, thank you everyone for your patience as well through